Alright, welcome to the third video in my wild networking series where I focus on network engineering as you might see it in the wild, such as on the job or through your own curiosity, as opposed to for a certification exam. So for this video I will be learning about Arp scaling. So there's a RFC here. Looks like there's, so the RFC is 7342. Looks like it's hosted on multiple URLs, but regardless of the one I go to, it looks like it's still going to be the same. Here's some pictures here that might be helpful as I go through the RFC, but the main thing I'm going to be focusing on is the RFC. So this is practices for scaling ARP and neighbor discovery in large data centers. This memo documents some operational practices that allow ARP and neighbor discovery to scale in data center environments. And I'll shrink, I usually have my camera be big when I give an intro and then shrink it down and share my screen, so I'll be sure to do that. Okay. And this is, so this is one thing I definitely wanted to make a few videos on, is what all of this meta information means for an RFC, because, and this is a great video for wild networking too, because reading RFCs when there's a brand new protocol out tomorrow, you know, and you're on the job, you can't really just sit around and wait for Cisco Press or O'Reilly Media to write a book on it. You gotta get it as soon as you can get it, and the RFC is going to be the original source for it. So learning how to read an RFC and how to interpret this metadata, so I can see this is an independent submission, I can see that it's informational, I can see who wrote it, all of that is very, very meaningful. And unfortunately I am kind of in the boat where like it's all starting to, because I launched my career in 2015, and I kind of, you know, I did that with Cisco networking, going to school with Cisco networking, so I didn't get here by reading RFCs, but that's because I had a long ways to go. Now that I'm more, you know, on the edge of things, this is something I'm going to need to be doing more and more. So I'm learning this myself, but I'll definitely make this a part of this series as well, reading RFCs and understanding which RFCs are important to read. This document is not an Internet Standards Track specification. It is published for informational purposes. This is a contribution to the RFC series, independently of any other RFC stream. The RFC editor has chosen to publish this document at its discretion and makes no statement about its value for implementation or deployment. Documents approved for publication by the RFC editor are not a candidate for any level of Internet standard. Information about the current status of this document, any errata, and how to provide feedback on it may be obtained here. Let's see if there's some errata. Now, you usually would say like errata exist if there's some errata, but if there's a mistake in it, we can see what the mistake is and how it was corrected by going to this link. Oh, and this is nice too. It looks like we can get different formats of it as well. Here's just the text format, but if we want it in a PDF for whatever reason, we can put it in a PDF. One format that would be really useful is, well, it's already HTML format. Oh, and up here it looks like you can change it as well. I have this Spritz It extension so I can read things at a glance like that, but I haven't been using that a lot lately. Okay, so let's review the table of contents. We're gonna, yeah, so this is for data center network designs, something I'm more and more getting into because data centers are just a huge part of networking. But I definitely came from a service provider background, so a lot of this is going to be new for me. Okay, so introduction. This memo documents some operational practices that allow ARP, or neighbor discovery for IPv6, to scale in data center environments. Described in RFC 6820. Oh, perfect. Yeah, this will be a good one to read as well. Oh, I actually wanted that Internet Standards. No, actually, let's keep our eyes on the prize here. So, described in RFC 6820, the increasing trend of rapid workload shifting and server virtualization in modern data centers requires servers to be loaded or reloaded with different virtual machines, VMs, or applications at different times. Different VMs residing on one physical server may have different IP addresses or may even be in different IP subnets. In order to allow a physical server to be loaded with VMs in different subnets, or allow VMs to be moved to different server racks without IP address reconfiguration, the networks need to enable multiple broadcast domains, many VLANs, on the interfaces of L2/L3 boundary routers and top of rack TOR switches to allow some subnets to span multiple router ports. Note, L2/L3 boundary routers, as discussed in this document, are capable of forwarding IEEE 802.1 Ethernet frames, layer 2, without a media access control MAC header change. When subnets span multiple ports of those routers, they still fall under the category of single link subnets, specifically the multi-access link model recommended by RFC 4903. Oh. Okay. They are different from the multi-link subnets described in multi-link and RFC 4903. What's multi-link? Oh, that's another section of this. Oh, it's like a book or something. Multi-link subnet support in IPv6. So it's not an RFC, it's like a book. Oh, it's a IETF. See, this is what I mentioned earlier that I want to eventually. Oh, okay. Well, this looks like, yeah, this is it. Okay. Okay, so they are different from the multi-link subnets described in multi-link and RFC 4903 which refer to different physical media with the same prefix connected to one router. Within the multi-link subnet described in RFC 4903, layer 2 frames from one port cannot be natively forwarded to another port without a header change. Unfortunately, when the combined number of VMs or hosts in all those subnets is large, this can lead to address resolution. For example, IPv4 ARP and IPv6 neighbor discovery scaling issues. So address resolution, mapping the MAC addresses to the IP addresses, doing that at scale can be an issue when there are a lot of hosts being used in a subnet. There are three major issues associated with ARP/neighbor discovery address resolution protocols when subnets span multiple layer 2/layer 3 boundary router ports. And I laugh because ARP stands for address resolution protocol, so there are three major issues associated with address resolution protocols when subnets span multiple layer 2/layer 3 boundary router ports. The first one is the ARP/ND messages being flooded to many physical link segments, which can reduce bandwidth utilization for user traffic. Yeah, so this is pretty. Oh, you know what this is? Wait, is this just basic? Is this just talking about using VLANs? No, this is like a new one, isn't it? What's the date on this? Oh, 2014. Maybe this is just talking about using VLANs. Well, let's keep reading and we'll find out. Number two, the ARP/ND processing load impact on the L2/L3 boundary routers. Number three, in IPv4, every end station in a subnet receiving ARP broadcast messages from all other end stations in the subnet. IPv6 ND has eliminated this issue by using multicast. Yeah, so, yep. So let me go over the three issues again, make sure I understand them. The first issue is the ARP/ND messages being flooded to many physical link segments, which can reduce bandwidth utilization for user traffic. So that's pretty self-explanatory. The more traffic you have being used just for address resolution, the less traffic you have for downloading cat pictures. The second one, the ARP/ND processing load impact on the L2/L3 boundary routers. So that's another one that's pretty self-explanatory. If your device is being asked to map MAC addresses to IP addresses, it's going to do fine if it's asked to do it once, twice, 3 times, but 1,000,000 times, 2,000,000 times, 1,000,000,000, 1,000,000,000,000 on from there, it might have some problems processing that. And the third one is in IPv4, every end station in a subnet receiving ARP broadcast messages from all other end stations in the subnet. And it's not an issue for IPv6 since IPv6 is using multicast. But this one is a little bit, I think, less self-explanatory than the others because it's not just a matter of something being exhausted, essentially. It's a matter of too much information, I guess is the way I would say. Well, not even that. It's like it's like talking, to it's like going to a grocery store, seeing your neighbor, and saying, "Oh, hi Jim, I haven't talked to you in a while," and then pulling out a bullhorn and having a conversation with him that can be heard from like 5 miles out. Like that's what ARP does, because it uses broadcast messages to ask if a certain to ask what the MAC address is associated with the IP address. So what it does is it sends out a broadcast message, and it says who has this IP address. Here's my MAC address. You can tell me, you can send it back to me. Just let me know what your MAC address is. Here's my IP address, of course. Here's my MAC address, so update your table with that, and then send me back the missing piece of information I need. I'll update my table, and then we'll not stop using this bullhorn anymore. We'll just communicate unicast. So that's obviously something that's not scalable as well. Sending out these ARP broadcasts, the more devices you have sending out broadcasts through ARP, the more extra traffic, the more traffic that is being used that isn't traffic that the user benefits from. So it's kind of similar to the first one, but it's more specific in that it's about the mechanism that ARP uses, and this one only applies to IPv4 because IPv6 just uses a different mechanism. It uses multicast instead of broadcast. Since the majority of data center servers are moving towards 1G or 100G ports, the bandwidth taken by ARP/ND messages, even when flooded to all physical links, becomes negligible compared to the link bandwidth. In addition, IGMP/multicast listener discovery. Oh man, I'm having flashbacks from my JNC IESP now, learning about that. That was an absolute nightmare. But the good news is I know what they're talking about. It just gives me chills. Snooping, RFC 4561, can further reduce the ND multicast traffic to some physical link segments. As modern servers' computing power increases, the processing taken by a large amount of ARP broadcast messages becomes less significant to servers. For example, lab testing shows that 2,000 ARP requests per second only takes 2% of a single core CPU server, and most of these servers are my home lab server is a hex core, so I've got 12 cores in just my old refurbished cheap home lab. Therefore, the impact of ARP broadcasts to end stations is not significant on today's servers. Statistics provided by Merit Network, ARMD statistics, have shown that the major impact of a large number of mobile VMs in a data center is on the L2/L3 boundary routers, i.e. issue 2 above. So it sounds like issue 1 really isn't that big of a deal, because nowadays you're going to be dealing with 1 gigabit links, 10 gigabit links, probably even bundles where you've got 40 gigabit links, 100. It's getting fast. That's the point of these developments in network engineering is to get more bandwidth, things faster. So having a 10 gig link in every home is definitely a goal right now. I have a jack where I can get a 1 gig fiber connection to my apartment, but I have tried calling the company offering it that I will leave unnamed, and the process to sign up for it has been unimaginably difficult. All right, so the first one is not that big of an issue because, as I mentioned, in my own apartment, if the process for signing up for it were simpler, I would have a gig to my apartment right now. So the amount of bandwidth taken up by these messages is significant when you're dealing with low-level links, especially if you were dealing with like a T line, something like that, really low bandwidth links. But today's internet have faster physical link segments. The third one is also not as significant because there have been so the third one is also not that significant because when an end station receives an ARP request, even though it is they receive an ARP request from everyone requesting an ARP request because it's broadcast, the end station, which is like a server or something, it's not difficult to serve an ARP request, to just map the IP address to the MAC address. It takes very little processing power. So even though you're piling on, you're sending millions, billions, trillions of requests, even a single core CPU server nowadays, 2,000 ARP requests is only 2%. So that's so that's not as big of a concern. So the biggest concern is the ARP/ND processing load impact on the L2/L3 boundary routers. This memo documents some simple practices that can scale ARP/ND in a data center environment, especially in reducing processing loads to L2/L3 boundary routers. Terminology. This document reuses much of the terminology from RFC 6820. Many of the definitions are presented here to aid the reader. So the first definition is ARP. This is IPv4 address resolution protocol. Then we have aggregation switch, a layer 2 switch connecting top of rack switches. And we have a bridge. This is an IEEE 802.1q, which is the VLAN tags. This means it can process VLAN tags. Compliant device. In this document, the term bridge is used interchangeably with layer 2 switch. DC, data center. DA, destination address. End station, VM or physical server, whose address is either the destination or the source of a data frame. EOR, end of row switches in a data center. NA, IPv6 neighbor advertisement. ND, IPv6 neighbor discovery. NS, IPv6 neighbor solicitation. SA, source address. TOR, top of rack switch, also known as access switch. UNA, IPv6 unsolicited neighbor advertisement. VM, virtual machine. Subnet, refers to the multi-access link subnet, referenced by RFC 4093. Okay, so we've got some common DC network designs. Some common network designs for a data center include 1, Layer 3 connectivity to the access switch, number 2. Large layer 2, and number 3, overlay models. There is no single network design that fits all cases. The following sections document some of the common practices to scale address resolution under each network design. So the first network design is layer 3 connectivity to the access switch. Layer 3 to access switches. This network design configures layer 3 to the access switches, effectively making the access switches the L2/L3 boundary routers for the attached VMs. As described in RFC 6820, many data centers are architected so that ARP/ND broadcast/multicast messages are confined to a few ports interfaces of the access switches, for example, the top of the rack switches. Another variant of the layer 3 solution is a layer 3 infrastructure configured all the way to servers or even to the VMs, which confines the ARP/ND broadcast/multicast messages to the small number of VMs within the server. An advantage of this design is both ARP and ND scale well. There is no address resolution in this design. What? Yeah, there is. Why do you need ARP then? Okay, I'm confused by that because there is address. Oh, I see. No. Wait, layer 3. Oh, I see. Oh, okay. I think I understand now. Yeah. But yeah, so this video here will explain what that means.
Alright, welcome back. It's Back to the Basics. I'm Sean Barr, and today we are talking about layer 3. Let's go!
I should watch this under my other channel.
At the access layer, you may be asking yourself, what is that? Well, in other videos we've talked a little bit about architecture, network architecture, and there being 3 layers: core, distribution, and access. And so starting from the access layer is where you plug in all your peripherals, the laptops, the APs, the printers, all the end user devices get connected at the access layer. At the distribution layer is typically where your access layer switches are connecting to your distribution layer switches. All of those get connected and aggregated at the distribution layer, and then those connect up to the core where traditionally a lot of the layer 3 routing decisions are made. So when we talk a little bit about routing at the access layer, it's really around getting some benefits of the uplinks. Now, going back in time, traditionally, if you had uplinks going to a distribution layer, or in an instance of a collapsed core, where you have your distribution layer and your core combined, those uplinks to side A and side B, let's say you had core 1 and core 2, those 2 links would not be unified. So they came up with this idea called routing at the access layer, where we enabled layer 3 on the access layer switches, and then we leverage both uplinks to the core through routing protocols. So now with the age of multi-chassis ether channel, meaning we've got a core A and core B, and they're connected together to appear as one chassis, and down at the access layer we can do the same, and we can now have multi-chassis ether channel, which basically at layer 2 combines 2 uplinks and makes them look as one. We just said a lot of crazy technical jargon, but essentially the difference between layer 3 at the access layer and layer 2 at the access layer is essentially, where is the routing decision made? Are we bridging up to the core and then making a layer 3 routing decision, or are we making a layer 3 routing decision at the access layer? You get a lot of benefits from it because from layer 3 of the access, because you don't have broadcasts spanning the network. It's really only IP to IP communication. The downside of it is that you can't span a layer 2 segment across IDFs or across switching environments if you wanted to, let's say, bridge wireless traffic. So you really have to make a decision. What are you going to be doing in the network?
Okay, so those are really good, two good things to note. So let's. I'm going to take a moment here and write that down as a note here. I'm keeping notes here. So yeah, I took this out of that list up there, and oops, there you go. Arp scaling. Yeah, so for ARP scaling, one of the first big decisions you need to make is, do you want layer 3, do you want your your frames, frames are what's exchanged at layer 2, to go all the way up to your to go beyond your access layer up to the other switches, and then have those switches route them, or do you want them to be routed as soon as they come in as packets? So pretty much your entire networking work is processing IP packets, making routing decisions, and the place on your network where your traffic is as frames is very limited. So layer 3 extends either all the way to the access layer or not. So those are the first. That's the first decision you want to make, and we can see that more clearly here in this diagram. If we leave the access layer at layer 2, we've left the routing to these devices here. So now one of the trade-offs you can get with this, just speaking on my own, what I believe here is you're talking about different devices. So a layer 3 capable switch, you know, it's going to be a nicer switch. So yeah, so a multi-layer switch, layer 3, we've got an Amazon there. So, and then a layer 2 switch. Let's see what Amazon's got for that. Yeah, layer 2 switches. So here's a layer 2 switch for $141. Okay, that's interesting. The same switch is listed there. So it looks like I'm not actually getting a difference here. Okay. Huh, that's interesting. But anyways, this is definitely going to be a big part of the decision-making process. What actual gear am I looking at ordering? Is that gear, is that a layer 3 switch capable of both layer 2 and layer 3? Is it just a only capable of layer 2? Is it only capable of layer 3? So these decisions here, whether or not to extend it down, shape the kind of purchasing decisions you'll need to make for the gear on the network. So you can see here's the two differences. These down here are very different devices. They're even using different icons for it.
network. Why would I want to do layer 3 at the access layer? Maybe I want that routing and resiliency and that control of my uplinks. Up to the core, or maybe I need the flexibility of moving layer 2 boundaries across IDFs. If I want that, then I've got to do layer.
IDFs? What are IDFs?
Layer 2 at the access. We're going to do a whole tech talk.
Yeah, and that's an advantage too. If you have IPs on your uplinks, because for in-band management you need an IP. So if you have layer 2 on those, you only get that one management IP address on the VLAN interface. So if you mess up ACL, or if you try to do something fancy, if it's layer 3, you can try to get in through the IP on the uplink, and you don't have to just completely rely on the management IP that you set up on a loopback interface or a management VLAN. Okay, so let's see here.
On designing networks and going into all the details, but this gives you a little sense of what's the difference between layer 2 at the access, what is layer 3 at the access, and if you had any questions and something I said in this crazy technical blah blah blah, leave a comment, like, subscribe, and we will see you on the next Back to the Basics. Thanks for watching! For some reason, I decided to challenge Ken.
Okay, so I don't think this is good. So we'll close that. This is great. You can see all the pictures here. We've got yeah, all the different kinds of. So here we have layer 2 up here instead of down there. So the video did bring up some good things. So yeah, so it determines the kind of devices you can have at the access. I would say, now what do you say there was a IDF? I'm gonna keep that here. Okay, so IDFs. Intermediate distribution frame. Oh, okay. So if you so let me just say this. If there's a special technology or device that requires you to have layer 2 that prevents you from having layer 3 extend down to the access layer, you have to use layer 2 at the access layer, obviously. But you know, one of the big problems you can have as a designing a network is not realizing that there is a device like that. So that's definitely always the question to be asking is there anything, if I'm making a design decision on do I design the access layer to be layer 3 or layer 2, is there anything that prevents it from being layer 3 or from being layer 2? Because even if there are 10 pros and 2 cons for making it layer 2, but there's 2 pros and 10 cons for making it layer 3, if one of the cons is you just can't do it or it'll cost extra, you know, and replacing that is not an option or would make it more expensive. Basically, not all pros and cons are created equal, and there could be a situation where, yeah, layer 3 at the axis is the best way, it's the way we want to do it, but it would mean replacing this system, which would cost this much and that amount of time, and meanwhile it works perfect, we just don't get this extra thing, and how much is that thing really, how much does that thing actually like what is the justification for placing it? Because of course it can be replaced if there's the time and the money to do that, but just simply using layer 2 at the edge instead of layer 3 might be a better way. Okay, so that video was actually pretty, I'm pretty satisfied with that. I got a good answer of what's the difference between extending layer 3 down to the axis layer or not. The difference is the kind of gear you can have at the axis layer. If you extend it down there, you're going to need to have multi-layer switches, but you can have your uplinks be layer 3, which will give you like a different kind of, it'll give you more control over how your traffic is load balanced across the edge, because you can make like routing decisions and use routes to move the traffic instead of just MAC address tables, and you can probably do like private VLANs, stuff like that, but the layer 3 all the way down to the axis layer, yep, you get extra resiliency and control because you've got IPs and you can use dynamic routing protocols and work with a routing table instead of a MAC address table. Okay, so let's take another detour and read this article here. So, routed or switched access layer, why not both? A major consideration when designing an enterprise network is whether traffic at the access layer will be switched or routed toward the distribution layer. Placing multi-layer switches in the access layer yields significant advantages. Chief among them is the ability to fully utilize all uplinks to the distribution layer, as loops are no longer broken by STP. Ah, okay, so that one, yep, so, yeah. Yeah, so if you have it layer 2, so layer 2 is basically the bad way, but, you know, as he said in the video, it might be necessary in some cases, depending if you have dependencies. However, many organizations opt to stick with simple switched layer 2 access schemes to support one or two legacy applications, exactly, which require a direct layer 2 path to a server or management station, or to maintain a common subnet for similar devices scattered about multiple access blocks. For example, security systems or environmental monitors. So that's the big thing. Since we're at layer 2 here, down to the access, we've got to have spanning tree, because they're all in one broadcast domain, so there will be a loop. If I were to, we can just ignore this link here and just think about these 4 links. If I were to move this device up here like that, with these 4 links, we would have a box. So there's a loop. Yeah, you can see kind of like a bow tie here loop between all 4 of these. That's not going to work. It's just going to keep looping and looping and looping until the devices fail. So one of these links are going to have to always be disabled by spanning tree. If you have layer 2 stop at the uplinks to the core. So if the access layer uplinks are passing frames instead of packets, instead of routing, you've got to have one of those uplinks blocked. Otherwise, you'll have a broadcast storm. Here you can have all of the uplinks active, so you get an extra link. In such a situation, it's quite feasible to extend both routed and switched connectivity to the access layer, provided you have multi-layer access switches such as Catalyst 3550, 3560, or 3750. Within the IEEE 802.1q trunks between distribution switches and access switches, one VLAN can be designated as a routed point-to-point link, and one or more additional VLANs can be added for traditional layer 2 connectivity. Okay, so here we've got our access layer. What the hell? Oh, I see. Huh. Okay, so here you can have VLAN interfaces with IPs on them. So you don't have to assign a IP to each link like that. You can just assign it to the VLAN interface. And then you can have trunks like this and split them up into VLANs that way. So VLAN 20 could be going there and there, and VLAN 10 could be going there and there. In this hybrid L2/L3 access design, VLANs carrying normal routable traffic are terminated directly on the access switches, as in the L3 design shown earlier. Traffic from end hosts is routed out of these VLANs and onto one of the point-to-point VLANs shared with the distribution switches. In our example above, traffic from VLANs 100 and 101 is routed from the access switch to the distribution switch via VLAN 2, a point-to-point/30 link. A separate point-to-point VLAN must be created for each physical link between an access switch and a distribution switch. This design allows us to still extend some VLANs for legacy non-routable applications up to the distribution layer. In the example above, VLAN 99 extends to the distribution layer, sharing the same 802.1q trunks as the point-to-point VLANs. We can see how this hybrid access design allows us to have our cake and eat it too. It's worth noting, however, that this design reinforces the need for independent layer 2 and layer 3 documentation and topology drawings. I've written a follow-up article to better explain the design discussed here and address some of the comments below. Okay, perfect. Yeah, I think I would like to read this follow-up article as well. So let me save some of these articles in my notes here. Okay, and I'm at the 10-minute warning here, so I don't want to go more than an hour per video. That's just a lot. Alright, so this is the hybrid access layer design revisited. A few months ago, I wrote an article explaining the benefits of a hybrid enterprise access edge design, which allows for both routed and switched traffic at the access layer. Reading over some of the comments on that post, it's clear a number of users did not understand the motivation behind such a design. I'm in that boat too, actually. I didn't think that article was very clear. This is partly my fault, as I underestimated the need for more illustrative topology diagrams. So today I'm taking another shot at it in an effort to both convey the idea more clearly and to address concerns based in comments on the first post, raised in comments on the first post. So layer 2 versus layer 3 at the access edge. Legacy enterprise campus designs employ routed links only within the core and between the core and distribution layers of a network. The bottom access layer functions entirely at layer 2 with VLANs extended from distribution switches down to the end hosts. Okay, so I think this is the access layer here. This is off to, I wish he had labeled that here. And this whole article is meant to clarify that. Because he's talking about the core and distribution, so but I think this is the access and distribution, and this is how it's done traditionally. But you can, yeah, so now you can see, yeah, you can change it, so instead of doing it this way, you do it this way. So this is the distribution, this is the access, same here. Routed SVIs, VLAN interfaces configured on the distribution switches serve as end hosts' default gateways. This design works well enough, but does not provide true load balancing across access distribution links due to L2 topology limitations, spanning tree blocking. That's the big one. Yep. Okay. So you got to think about the fact that when you're operating at L2, you're always going to have a broadcast storm unless you don't have a topology that allows for one. And the way you get that automatically without having to design it is by enabling spanning tree. Then along came multi-layer switches like the Catalyst 3550 and 3560/3750, which made it possible to extend layer 3 functionality down to the access layer. The major benefits of such a design were the possibility of true equal cost load balancing across access distribution links and faster failover time. So you couldn't have a path through this old one that would have an equal cost, because you'd have to have one of these links blocked, or else there would be a loop. You couldn't have traffic, all of these links here that I'm hovering over live, or else the traffic would just continue to loop over them until the devices had issues. So you would block one of them like this, but now there's not an equal cost path because one of these links is blocked. A third recently developed access edge design employs virtual switches and multi-chassis link aggregation at the distribution edge. However, we'll only be looking at the first two designs mentioned in this article. Of the two designs discussed above, the latter is generally preferred. However, many organizations find themselves bound to the layer 2 design in order to support legacy systems which require a contiguous L2 domain throughout large portions of the network. Such examples might include legacy FAT wireless access points, security devices, HVAC sensors, and so on. In these cases, many organizations opt to implement a hybrid design, which is able to provide L2 connectivity where required and L3 connectivity where possible. A hybrid approach. We can support both L2 and L3 connectivity at the access layer by implementing point-to-point links within VLANs on the access distribution IEEE 802.1q trunk links and relocating SPIs for the routed VLANs down to the access layer. Okay, so now we've got VLAN 101, 102, and 103. Here we've got same thing on our access layer. Okay. I'm almost wondering if he has a typo here. Was this meant to be 101 and no? Okay, I'm not understanding this drawing here. In the above topology, VLANs 101, 102, and 103 each terminate on their respective access switches. VLAN 5 is carried through the 802.1q trunks up to the distribution layer where it can span multiple access switches. VLANs 10 and 11 each serve as independent point-to-point links configured with an IPv4/31 between the first access switch and either of the two upstream distribution switches. Both of the other access switches also have point-to-point VLANs configured to the distribution switches for a total of 6 point-to-point links between the access and distribution layers. 1, 2, 3, 4, 5. Oh yeah. So all of these are now point-to-point because they've each got their own VLAN. A configuration on the leftmost access switch in the above example might look like this. So we're going to have the oh yeah, so here's the legacy device that depends on the... Oh, I see. Okay, so so using this, you can provide the modern... I gotta turn on my light here. Oh yeah, I'm wearing my... Yeah, oh no, I am wearing dress pants. I thought it was... okay. So, let me think here. Right, so you can have a design where you have layer 3 at the edge, even if you have a device that depends on layer 2 being at the edge, because you can just create a special VLAN for that device and give it its layer 2 connection up to the spine. So we can see here, or to the distribution layer. So we can see here that the first edge switch here that's using VLAN 101 as its SVI does have a device like that. It's a legacy device that depends on there being layer 2 all the way down here. So we give it layer 2 by putting it on this VLAN 5, and then we're trunking VLAN 5 up through there. Yeah, and now we've got our point-to-point subnets here, but you see we don't have an interface for VLAN 5 because that's the yep. So here, we can see we've put that. We've given it that special pathway. VLAN 5 traffic from one access switch to another is switched into the distribution layer and back down, never leaving VLAN 5. The path from source to destination is a single hop. Yep, perfect, okay. Traffic from VLAN 101 to VLAN 102 is removed from the access VLAN and routed out of the SVI on the access switch. From there, it is routed via the point-to-point VLAN in the trunk up to the distribution switch and via a second point-to-point link down to the access switch for VLAN 102. The path from source to destination is 3 hops in length. Okay, so here's the questions that the previous one had that he tried to, that he's going to just specifically answer here. Why not simply go pure layer 3 links to the access edge? If you can, do it. Again, this design is intended for situations where there still exists a requirement for L2 access between points within the access layer. How well will this scale? If implemented properly, very well. VLAN IDs used for access layer SVIs can be reused in a standard template, such that, for example, VLAN 101 is for workstations, 102 is for wireless access points, etc. Only the IP subnets need to be unique, but you can reuse the VLANs across on each device because VLANs are locally significant only. This design seems too complex to manage and troubleshoot. If you can manage a layer 2 network and you can manage a layer 3 network, you can manage this design. If you can't manage either of the first 2 networks, it's time to hit the books or look for a new job. Vendor X doesn't recommend this design. That's because this isn't an ideal solution, as already stated. The ideal solution is to remove the requirement for L2 access at the edge. Network design is a compromise between the ideal and the practical, heavily in favor of the practical. Love it. This is, I really feel like the last hour has been just so good. A loop within the layer 2 topology can still bring down the network. Again, this solution does not try to remove the downsides of a layer 2 topology. It simply allows us to take advantage of the benefits of a layer 3 access edge where we can, to remove the STP limitations, remove the need for L2 access. It is also worth noting that while spanning tree protocol runs on the point-to-point VLANs between the access and distribution layers, these links by definition cannot form a loop, erroneous configuration issues aside. And that's, yeah, and that's a good reason to leave it on there, because even though it can't form a loop, misconfiguration, you have spanning tree off, you got a broadcast storm instead of just a blocked link that you probably can fix in band. Maybe it'll be the uplink that gets blocked, but no, if you have a loop, yeah, if you have a loop, you're always going to have a uplink that is unblocked, I think. Yeah. Okay, so users will want to move among access blocks and keep their IP address. Practical impediments to the roaming of wired clients aside, Only the L2 VLANs, VLAN 5 in the example above, will support this. Generally speaking, end users should always reside on the VLANs terminated on access layer switches. Further, it is up to your organization, not your network design, to decide on and enforce network policy. How should VTP domains be arranged? Unless you have a very good reason to use VTP, don't. Still, if you feel compelled to employ VTP, do so exercising the cautions you would on an all L2 access layer design. Yeah, in the modern day with APIs and NetMiko, Ansible, that sort of thing, there's just absolutely no reason to use VTP. Okay, so this is the layer 3 to access switches. According to the articles we just read, that is the preferred way to do it. This network design configures layer 3 to the access switches, effectively making the access switches the L2, L3 boundary routers for the attached VMs. As described in RFC 6820, many data centers are architected so that ARP/ND broadcast/multiclass messages are confined to a few ports, interfaces of the access switches. For example, the top of rack switches. Another variant of the layer 3 solution is a layer 3 architecture configured all the way to the servers or even to the VMs, which confines the ARP/ND broadcast/multicast messages to the small number of VMs within the server. The advantage is both ARP and ND scale well. There is no address resolution in this design. Okay, so this was actually really confusing when I first read it, but now I understand it more. When you use a topology that has layer 3 extend down to the access switches, ARP and ND scale very well, and that's because you don't need to send your ARP or ND messages any deeper than the access, because that's what you're doing. You're having here. So if you didn't have it extending down here, your ARP requests would go all the way up to your distribution. Here they're just traveling along these links, and they're and as you add more switches, so if we add another access switch here, links, now there's all these extra links they're going over. Here, as you add more switches, since they don't go all the way up to the distribution layer anymore, they get cut off at the access, it scales much more, it scales better if you're from Louisiana. The main disadvantage of this network design occurs during VM movement. During VM movement, either VMs need an address change or switches/routers need a configuration change when the VMs are moved to different locations. Oh, I see. Oh, okay. Summary: this solution is more suitable to data centers that have a static workload or network operators who can reconfigure IP addresses on switches before any workload change. No protocol changes are suggested. Okay, so that's another one disadvantage. Once you've got IPs involved, you've got to change the IPs and manage the IPs. So the alternative to that is, wait, what? Oh, they're not going to talk about the alternative to that. So, okay, so here's layer 2 practices to scale ARP/ND, practices to alleviate ARP/ND burden on L2/L3 boundary routers. The ARP/ND broadcast/multiclass messages in a layer 2 domain can negatively affect the L2/L3 boundary routers, especially with a large number of VMs and subnets. This section describes some commonly used practices for reducing the ARP/ND processing required on L2/L3 boundary routers. And it looks like I barely got through this, and yeah, so I've got probably another hour of reading to do on this. So I'm gonna cut myself some slack here. I need to get through all of this. So if I just, burn myself out at a 7-hour video now, I'm just concerned that later I won't be able to go. So let's see if I can use that technique that I saw on the Wikipedia page here. Oh, it works. Oh, no, it didn't work. Didn't work. No, that's just a Wikipedia thing. Okay. Well, okay. I mean, it looks like it's still, it accepts the, I can go to the page if I have this pound sign there. So I'll just save it like that in my notes here so that I remember where I left off. I'm not going to save this right now, I'll just leave it open. But yeah, I think that's going to be the end of the video today. I would like to keep going on this. This has been a really great use of time. I really think this is something I want to continue doing, but today I already did this for 2 hours, so maybe I can do an evening video or something like that for another hour, but for now that's going to be the end of this video. Stay tuned for the next one where I continue to read where I continue to read this RFC on Arp Scaling.